Swayam Prabha. Digital India. Educated India.
Good morning. So today we start with radicals in heterocyclic chemistry. I don't have to tell you that the organic chemistry began with radical chemistry. If you recall, that was in the first class, right? The halogenation of alkanes. Actually, for alkanes, there are not many reactions known in the literature. If you think about the alkane chemistry, you will have hardly a handful of organic reactions applicable to alkane chemistry, because all of us know that CH bonds are not easily functionalizable. So, one of the earliest and useful reaction is the halogenation of alkanes like chlorination, brominations, etc. Okay. Similarly, the radical reactions in heterocyclic chemistry also is very useful, and but is not talked well as a subject. And in heterocyclic chemistry, radical could be very useful provided you know the subject, and it can produce normally carbon radical, nitrogen radical, oxygen radicals. We are actually concerned about all these three radicals, but primarily we are concerned about the radicals which are carbon, means carbon bearing radicals. Okay. And our starting example should be from a set of reactions. I like to focus on the reaction conditions which are applicable to the radical chemistry. In the first slide, what I will do, I will just give you 4 different examples with 4 different experimental conditions and their corresponding products. That will tell you the types of the reactions you can achieve, types of the reagents you can use, and of course, that also would set the example for the generation of carbon radicals. Then we will go to a very broadly used radical reactions organic chemistry, that is Minsky reactions. Very briefly I told you when we talked about the speciality of nitrogen. Okay. Let us look at a set of examples. This is a case of pyrimidine. You have substituted pyrimidine, you have these, and then you have to carefully note the reactions conditions. Reaction conditions are like this. You have all of us know what I am writing. If you do not know, I think I will just tell you later, but what is the nickname of the formula I wrote? Ethyl? No. No. It is a pretty well known in biochemistry. Right, ethyl pyruvate, and this is a reaction. Okay. So, you can see here, and the yield of the product, I will not write the product at the moment, yield of the product is 17%. Take another example very similar to the one I wrote. Once again, this is pyrimidine, but it is a methyl substituted one, and the reaction conditions are quite similar. It is ET, CO2, and I think all of us know what it is, ethyl glyoxylate. Then sodium perdisulfate, silver nitrate. So, these are the recipes. Then you have methylene chloride and water, and yield of the product what we will be getting is 83%. Then there is another reaction. I mean, all these actually leads to different publications. Then in this case, what you will find this set is little different: tertiary butyl hydroperoxide, ferrous sulfate, then of course, ferrous sulfate means ferrous sulfate hydrate, then benzaldehyde, sulfuric acid. So, all these is actually, then you have acetic acid and water, and the yield of the product is 61%. One more is this is not a pyrimidine, this is pyrazine. Pyrazine is a chloro, once again this is ethyl pyruvate, then 30% which is commonly used hydrogen peroxide, then ferrous sulfate, and of course, sulfuric acid, little sulfuric acid, sorry, I think maybe sulfuric acid should be there, and the solvent is toluene and water. So, all these examples actually belong to a reaction called Minsky reaction. Minsky reaction. What it is? How do you define Minsky reaction? Minsky reactions are the radical reactions. Radical reactions, reactions of carbon radicals. Carbon radicals to heterocyclic compounds. You have to, not the carbocyclic compounds. It is basically the domain of the heterocyclic chemistry. Okay. And what are the products that you have to find out? Okay. In the first case, the product is that means the skeletons remains as it is, then sorry, this nitrogen up here 1,3 nitrogen, phenyl, and what you will find in this case you are introducing an ester group directly, ester group directly. The same thing in the next example also would involve introduction of a direct ester group. Next example, so what you will find in the next example again a pyrimidine and the bromo, and in this case it is not the ester group, it is a COPH group, it is an acyl group, you can say acyl group. And the last one, and all of you can guess, the product is again ester substituted, ester substituted. Okay. What is the chemistry? Basically, you have to first note how to produce the radical. If you look at the first one, it is a pyruvate, right? It is pyruvate, and what else is required? See, if you look at the reaction condition, all of the reaction conditions would involve the presence of acid. So, that is the clue of the success of the Minsky reaction. Although this was observed by another French scientist quite a few years ago, Minsky observed, but that is the trick for the use of these radical reactions in heterocyclic chemistry. In heterocyclic chemistry, radical was not very successful, but one of the scientists found that if you protonate, the reaction takes faster, and also the reactions become little more regioselective, means you can get one regioisomer preferentially. Okay, that was the observation by one of the scientists called Duo or somebody from France, and then subsequently Minsky developed this in late 60s. Okay. So, for us we have to basically recognize the reaction conditions and the chemicals that are required. How to generate carbon radical from, let us say, ethyl pyruvate. If you look at the reagent is hydrogen peroxide. So, hydrogen peroxide means at some point the peroxide bond would be cleaved. So, in this case it is proposed that the pyruvate under the influence of acid, that means it carbonyl gets protonated, you get a sort of hydroperoxide kind of thing. Okay. And then you have ester groups here, and then all of us know what can happen next. This the peroxide linkage would be broken. So, you will have oxygen up here, and then you have carboxylic ester here. What next? Just basically this is where, that means this radical goes to this and the ester groups comes here. So, what you will find, this is CH3 and this is OH, and then what appears to be that you have a radical here at the ester carbonyl. So, that means it is a nice way of producing an ester carbonyl ester containing radical, and of course, then the question is where to attack, and all of us know that if you have a pyridine system, the carbon double bond nitrogen behaves like a Schiff's base. So, it undergoes addition to the electrophilic. That means, these are somewhat like nucleophilic radical compared to the pyridine system. So, if you go to the next one, the reaction condition is different. Go to the next one. What is the reaction condition? The glyoxylic acid monoester. Once again, this is one of the earliest reaction condition found by Minsky. All of these reagents are required. First of all, I think if I let us say give you the mechanism, that means the reaction set here, the reaction conditions here, E2 O2C and then oxalic acid, pyruvate glyoxylic acid and sodium 4-disulfate, silver nitrate, and what else? Yes, I think I missed probably acid. Acid should also be been there, because you have a nitrogen heterocycles. Whenever you have a nitrogen heterocycle, you have to always add an acid. And in this case, what happens? This 4-disulfate. If you per-disulfate, actually, if you bond wise, if you look write, it would look like so double bond oxygen, right? Now per-disulfate. So you have, I think, double bond oxygen minus, right? And then all of us can guess what happens. It breaks down to sulfate minus oxygen, and this, which is equivalent to sulfate radical anion. Okay. So, this radical anion actually picks up one more electron to become sulfate. From where? Actually, the simultaneously the glyoxylic acid. This is the trick here. The hydrogen has to be replaced by not many metals, actually. Silver. If you recall the decarboxylation of carboxylic acids, how is it performed? There are not many methods. That if you can come up with a nice clean methods at low temperature, let us say below 150 degree DMSO or DMF temperature, then you can get a nice publication. Just last 2-3 years, actually there are several publications. When you studied BSc, you used to use copper quinoline. copper quinoline is one of the standard technique. If you let us say you have benzoic acid, you want to convert benzoic acid to benzene, how do you do? Very old literature they used to heat with zinc oxide or zinc, something like that, I have forgotten, either zinc or zinc oxide. Okay. But then it came down that if you use copper and quinoline at high temperature, you can get decarboxylation. That is also used in heterocyclic chemistry. Then many of you know there is a little deviation of that is Hundt-Sticker reactions. Hundt-Sticker reaction, that is not a truly a decarboxylation reactions, but it along with that you brominate the carbon bearing the carboxylic acid. Okay. Then what else? There are not many methods. Okay. And there is one more very recently has come, that is palladium. If you replace the hydrogen by palladium, and there is a propensity that this carboxyl group would cleave to produce the corresponding decarboxylated product. Okay. In this case, this radical reaction is very specific to the silver. If you have a silver salt, then your sulphate radical that would immediately produce the corresponding decarboxylated carboxylic radical, that means in this case ester radical. Okay. So, once you have the ester radical, then you know the product. This ester would radical would add to the alpha position of the nitrogen. So, then let us say I will come back to this, let us look at the one more that this one, third example. What is the third example? In this case the combinations are tertiary butyl hydroperoxide, ferrous sulphate, and all of us by now know this Fenton's reagent, right. So, it produces the oxygen radical. Then there is a question. See, there are two substrates possible here. You have in this case benzaldehyde and you have carboxylic acid. So, that means carboxylic acid can form the corresponding ferrous salt and the benzaldehyde. Now, this the radical that is here you have these tertiary butyl peroxide or oxy radicals, sorry, tertiary butyl radical. Okay. Butyl oxy radical. Now, what sort of carbon radical do you expect? Okay. If you think of benzaldehyde, actually it can produce the radical here after the abstraction. Okay, let me give you here, right here. If you have benzaldehyde, so there is a possibility that the radical would that tertiary butyl oxy radical would abstract the proton and it can produce the corresponding pH, CH. So, oxocarbon radical. The other possibilities that it can this salt is produced with iron salt and that can be oxidized to corresponding to methyl radical. So, these are the two possible, that means one acyl radical, one methyl radical. Now, you have to know how to distinguish them, which one is more likely. Since answer is known, obvious it is the acyl radical. What is the driving force? Driving force is the once again the stability of the radical. So, the alpha like oxocarbonium ion cations, okay, carbon ion, and similarly here in this case these iron this carboxylate are not susceptible to oxidation to the oxidation with tertiary butyl hydroperoxide. Okay. So, this reaction set or the reaction conditions without silver is nicely suited for radical generation from the benzaldehyde. That you have to remember. That means, whenever you have hydroperoxide reagents without silver, there is a likelihood that it would produce radicals alpha to oxygen. So, we will have more examples. Let us look at the next one, the last one that is the fourth example. So, what is the fourth one means this one. So, now you can quickly find it out that you have hydrogen peroxide, ferrous sulphate. So, this combination means you have to have a hydroperoxide system, and then you have an ester group here. There is no carboxylic acid, that means, but so carboxylic acid should be ester or other radical should be generated through these hydroperoxide intermediates, semi or hemiacetal of these carbonyl compounds, and then eventually decomposing this. So, this basically gives you a rough idea about the types of the reaction conditions that are used in the Minsky reactions. And then maybe we will quickly, this is just an introduction, and then we will very quickly go to little bit of the radical chemistry in general. Why should we study radical chemistry? I have told you before, again just recapitulate what is the use of radical reactions, especially those who will be doing bioorganic chemistry, physical organic chemistry. Radical chemistry is very useful. In fact, the biological system of radical chemistry is very useful, right. Many times people say superoxide, dismutivase and all these things. And then inflammation. Inflammation is one of the serious diseases, right. Do you understand what is the meaning of inflammations? Inflammations. Swelling, that is basically the symptom. But in biological term, one of the commonest inflammation is due to the production of prostaglandins. Prostaglandins. If you have headache, you have severe itching everywhere, I mean whatever, many kinds of inflammations there. They are due to the production of prostaglandin in cells, and then that prostaglandin is produced from again a weak C20 fatty acid. What is the name of the fatty acid? Bolo. I think I thought you have studied all these. Krishna, arachidonic acid. Have you heard? Arachidonic acid. Okay. If you have not heard, you go to the any standard textbook, Morrison Boyd, Solomon's, anywhere. There is a big nice chapter actually. The arachidonic acid actually gives rise to prostaglandin. Most of the prostaglandin will have C20 carbon. Okay, this is due to the presence of or rather superoxide dismutase, which causes decompositions or which introduce oxygen radicals or which participate in introduction of oxygen in the biological system. Okay. So, that means what I am trying to say, radical chemistry is very useful in biological system and elsewhere. Many of you know polymer chemistry also. A series of a lot of polymers are produced by using radical chemistry. So, but what is the remarkable about polymer radical chemistry? What is the specialty? There are quite a few specialty. Let us say, in fact, most of the organic chemistry laboratory, when you go, you dry THF by putting sodium and benzophenone. Why benzophenone? Indicator. Very good. So it indicates. It also signifies something. Radical could be of sufficient stability. That means, if you remove moisture, if you remove oxygen rather, then it could be stable. There are many now, by now all of you know the radical even could be stable in air, and that means they are not that sensitive. So, depending on the situation, it could be very sensitive to oxygen and water, but again there are cases where radical could be very stable even in water. That is the beauty. Biological system means we have full of water only in body. So, in spite of all having all sorts of organic compounds also and then plenty of water, the radical could be very stable, very stable. So, that means the radical reactions can be run in the presence of water, in the presence of oxygen. Many reactions are just done in the open flasks. Okay. So, that is one of the major reasons why radical chemistry should be popular or rather should be made popular. Then there are radical, as you have noted in the earlier reaction conditions, sulfuric acids are deliberately added. Sulfuric acid is deliberately added. What does it mean? That means the radicals are inert to the acids. So, similarly also there are conditions where they are also insensitive to bases. Then next most important from the chemist points of view, that normally the radicals do not induce any elimination reaction, that is important. If you have a carbanion and the and the alpha beta positions are having a leaving group, then eliminations are most likely reactions, but in case of radical you do not see such things. Okay. Disadvantage is very difficult to actually predict. That means, we have understood carbonium chemistry very nicely, we have understood carbanion chemistry very nicely, but radical chemistry is not routinely understood. So, what you have to do, you have to have little experience from the examples and then typical patterns of the radical reactions. So, we have given you a set of reactions. Then let me give you just a little, that is the reason why you have to have something in mind. Now, let us say I will give you a set of precursors that that ought to be remembered. Let us say which are the precursors that are often used in radical chemistry, precursors. Let us say, then I will write some of the reagent sets. We have already said some, and then we will have something, and then the groups that are added to the heterocycles, groups I think added to heterocycles. So, that is the reason you have that. I mean, all of these basically are centered around the information about the carbon radicals. For example, you want to produce carbon radical, a carboxylic acid is sufficient, carboxylic acid is sufficient. And what is the condition? We have already said that. What should be the condition now? By now all of us know what is the condition. Carboxylic acid condition means first thing that you have to come to this is, it could be potassium pardisulfate, sodium pardisulfate, ammonium pardisulfate, and then one of these pardisulfate, let us say potassium pardisulfate. And what else? These are all inorganic compounds. So, you have to have water, and so this is and often always it is also sulfuric acid. You can guess sulfuric acid or TFA. These are meant for the heterocycles. Yeah, the heterocyclic nitrogens are protonated. So, it becomes the reaction becomes more regioselective, and so that way that this is it. And then this silver salt is prone to oxidation with potassium pardisulfate. So, once you know this, then the carboxylic acid could be taken as a substrate. Then and very fortunately, or rather very importantly, then Rx simple halides. How to generate radical from halides? Alkane? No, you have an alkyl bromide, let us say. Rx means it could be iodine, it could be bromine. How do you generate? Not really. Once again, you can use this Fenton's system, hydrogen peroxide and ferrous sulfate, then of course, sulfuric acid has to be there, and then solvent, it could be DMSO and water. And only then there are reactions conditions also R3. I mean, these are I am trying to basically list some of these alkyl radical generating precursors. This is one, trialkyl radicals, trialkyl boron. Trialkyl borons also are very useful precursor for generation of R radical, and earliest examples would involve reactions of these trialkyl borons with oxygen. In in the presence of oxygen, this is a mechanism, do not ask me the mechanism is too complicated, but if you have just oxygen contamination, it would generate the corresponding R radical. And the latest one, the 2011, I mean is quite interestingly boronic acid. Who discovered boronic acid? Generation of boronic radical from boronic acid. One very young scientist, he is below 40, on in the nose, Phil Warren. Okay. Only last year he produced, he had published series of papers in which he produced nice radicals from these boronic acids. I mean boronic acid has been known for Suzuki reaction, but it came to his mind that okay, this could be also a useful precursor, and under the very similar conditions. I will give you examples. Okay, very similar conditions, like but not silver nitrate, but it's just ammonium perdisulfate should be sufficient. Hopefully, I have to see exact. Okay. Then you have already seen that this pyruvic acid, if you have pyruvic acid, then it would give rise to, it will deliver this acyl unit. Then you have also seen that if you have ethyl pyruvate and under the influence of Fenton's conditions, it will provide the carboxylic ester. And similarly, if you have let us say methanol and what should be the radical? The radical, I mean again Fenton's reagent, and what is the substituent that would be provided by this? It is this CH2OH. This is to be noted actually. This is a very important actually guideline. This last example, methanol would give CH2OH. That means you have, if you look at methanol has we have 3 different kinds of bonds, right? Methanol has a bond, CH bond, carbon oxygen bond, and OH bond. And among the 3, which one is the weakest bond? This is to let us say I will give you OH in water, OH in ethanol, CC carbon bond in ethane, and then let us say CH bond in propane, and CBr bond in let us say ethyl bromide. All these things like you have studied in honors level. Which one is the weakest one? Which one is the strongest bond? Any idea? When I say strongest means strongest in terms of homolytic cleavage. So often we talk about the homolytic cleavage because that is easier to evaluate. So which one is the strongest bond? Carbon. Good. Any other answer? Any intelligent answer? No, we are talking about homolytic bond fission. Radical chemistry means homolytic bond fission. We have to know because we spend so much time in BSc learning, what is bond dissociation and how do you evaluate and what are the different trends, and then if you go to the JE etc., you will see this. It is a very important guideline actually. I mean the answer lies in the first slide. When I said the radical reactions are very useful, especially they can be carried out in water. That means if you have a carbon radical, it does not touch the water. So what does it mean? And actually I will give you the hints this morning. I forgot also, but today morning I had to copy the numbers. For water, the bond energy is 119 kilocalorie per mole, whereas carbon bond energy, what is the value? Average value. No way, it is 88, approx 88. Okay. So similarly, a carbon oxygen bond in methanol, it has a bond energy of 91.5. This is taken from Morrison, sorry, this what is that other book? Morrison word and Solomon's book. Okay. So, this basically tells you that these are all radical reactions this pattern, and so obviously the carbon hydrogen bond in methanol, carbon hydrogen bond strength in methanol I do not have it, but it is pretty low though, it is pretty low at the moment. Oh, I could not get it, but it is low simply because if you have a radical here, this should be stabilized by the oxygen lone pair. Okay. And there are others kind of a system. For example, many of you know there is a dilauryl peroxide is one of the reagents used in radical generation. Dilauryl peroxide, lauric acid, corresponding lauric acid. Lauric acid means how many carbon? This is commercially available and it is very cheap, plenty. Actually, it has 11 carbon atoms. Then there is also commonly used, especially by the polymer chemist, dicumyl peroxide. This is also pretty useful, but in combination with BF3 etherate. And I think we all understand the structure of dicumyl peroxide, right. So, basically corresponding the cumyl hydroperoxide dimerizes to give the corresponding. So, so these are basically the substrates and these are basically the reagents. And then you have to have different combinations here and there, and the corresponding, let us say I will give you one example, maybe even the amides could be let us say formamides, for example. Formamide could be also a substrate for radical generation, and all of you can guess the group that would be added to the heterocycle is corresponding amide, like ester. Directly you can introduce an amide. We gave you example in a class before. Okay. Let us from now onward, let us look at some of the typical examples, and the advantage. Like this was in the last year's exam. If you have isoquinoline and then treat this with isopropyl iodide, DMSO and hydrogen peroxide. So, what do you expect? I mean, it is a little difficult though. So, somewhere it will be some hydroperoxide will be generated. Actually, DMSO is this one, right. Then it goes to it undergoes oxidations with hydrogen peroxide, it goes to sulfonic acid, SFinic, and we have worked on sulfonic acid. They are very unstable. If you keep it in fridge, it will stay there for a month, then after that it decomposes. And but in the form of salt, it is pretty stable. It can be marketed, it can be shipped, it can be stored, and so this gives rise to corresponding alkyl group. If that is so, on the top combination would give you, this is equivalent to isopropyl carbon radical, and the reaction proceeds nicely, and all of us know the polarization is such that this isopropyl group would be attacking the one position of isoquinoline. So, and we have already okay. I think we have already said with acetaldehyde. We have already said. Let me give you one more example. The radical reactions also could be useful for enoxides, but to make it useful, you have to O-methylate first. and methylation can be done with trimethyl oxonium tetrafluoroborate, and this is all of us know this is a salt, pretty right. What is the name? Right, Meerwin salt is more reactive than corresponding methyl iodide, methyl sulfate, and it gives you this O methylated products. O methylated products CH3 here and chlorine. Now, this is basically salt here. Now, if you let us say particular combination now, methanol, and I will not give you the answer and simply heat it. What you will get eventually after all these demethylation etc., what you will get? You will get a nice introduction of direct introduction of CH2OH. So, what is the missing reagent? What is the missing reagent? We have given you all kinds of permutation combinations here. In this case, it is ammonium perdisulfate. So, it is a basically peroxide kind of thing. Any sort of peroxide, normally CH2OH is provided photochemically by photochemical reactions, but ionic in this case ammonium perdisulfate is sufficient. Let me give you one more example. This is an azole, azole with 3 nitrogen, then it has a side chain and it is a carboxylic acid side chain. Now, you treat this with let us say silver nitrate, again perdisulfate, and of course, an acid. Acid means to protonate the nitrogen, and so water has to be there because it is inorganic salt. Most of these reactions are done in a mixture of water and an organic solvent. So, you can guess what is the product, right. So, this recipe silver actually is meant to be suited for carboxylic acids. So, it will generate the decarboxylated carbon radical, that means radical will be generated here at the alpha position, and whenever you have a possibility of intramolecular reaction. So, the reaction would take place intramolecularly, and all of us can see that it will form this one. Also, it tells you something else, that even a 5-membered ring can be functionalized by carbon radical. So long we had been giving examples on the 6-membered ring. This is another example. The use of radical for the functionalization of 5-membered rings are not many though, but they could be useful provided they have a nitrogen in it. Okay. And let us say, I think we have given you many of these examples. Let me give you 1 or 2 more. This is the example. Maybe you can just take note of. Sorry, this was in 2010. JAX page number 131. This paper is by Phil Warren. Okay. What he noted reaction. If you begin with a substrate like quinoline, and then you can directly have a phenyl substituted quinoline. Particularly in this example, he could introduce the toluene portion. If you try to think about doing these transformations otherwise without involving radical chemistry, is how do you do? The basic, maybe you will be using the Cicci-Babin reaction. Chichi-Babin reaction corresponding toluene lithium compound, okay, right, that can add to this, and then you have to oxidize, etc. But then there could be a serious problem in those sort of reactions. What could be the other side reaction? In Chichi-Babin reaction for simple pyrrole is perfect chloride, but for substituted pyrrole substituted pyridines or other quinoline derivatives, right. So, that is called actually lateral lithiation, means side chain lithiation. Side chain lithiation can take place. So, Baran has of course come up with this different kind of solution. He has used this boronic acid, corresponding boronic acid, and then since it is an acid like carboxylic acid, also you will require silver nitrate, then potassium perdisulfate, and one more thing. What else? Like carboxylic acid, he has used sodium silver nitrate. Okay, perdisulfate is required for generating the sulfate ion radical, and acid. So, in this case he has cleverly used trifluoroacetic acid, and what you could get, you could get to this compound, So, I mean, if you look at, it is a very regius selective, that means only the 2 position is and that too directly in one step. So, that is the beauty. Let me give you one more example. This is from a natural product. I think I will write this structure. This is isoquinoline natural product, quinoline natural product, and I think can you guess? Actually, there are 2 carbons here, right? 2 carbons, 2 to 2 azaoctane, right? 2 to azaoctane, bicyclooctane. And what is it? I think all of you know. You have oxygen up here and this. This is 2 carbon. This is 2 carbon, this is here and here, this is 2 carbon. So, and this 1 nitrogen. So, it is 1 aza 2 to 2 octane, bicyclooctane. Okay. And then you have a vinyl group, you have a methoxy group. This is quinoline moiety, and all of us know what is the name. What is the name? You have to know. Quinine. Okay. Now, if you just apply the Baron's reactions with a substrate, I do not know why he has chosen this substrate. It is a substrate, it is a pretty big one, it is a diphenyl ether kind of linkage, and the corresponding boronic acid, and the recipe as before. So, as before, what, and if I or equivalent to, let us say I write AR BOH all twice. So, it will give rise to I mean, you can extrapolate, and what would be the product? The product would be here would be AR, and then rest as it is. So, you have oxygen up here, oxygen is here, this. That means, this is a very interesting example though, it is a remarkable example. Why it is so important? Why did I choose this example? In especially when you are trying to do biochemistry or any other advanced chemistry, you have to look for a reagent which are very selective. When I say selective means, of course, the selectivity fall under 3 different categories, right? regio, chemo, regio and stereo. So, 3 different categories, and in this case it is of course regio, as well, and there is no question of stereo, but it is very chemoselective, very chemoselective, means it did not, the radical that was generated from this here, the phenyl radical, it did not undergo addition to the double bond. Normally you know they have a radical, it undergoes addition to the carbon carbon double bond, it did not. Then what else would you have expected? What are the problem would you have anticipated? One could have been this radical would generate the double bond I said. Then if you recall, the radicals alpha to the nitrogens also is very stable. So, that could have been produced here, and alpha to the oxygen also, and as well as benzylic, that could have been also a possibility. All these possibilities have been not observed in this particular example. It has undergoes nice addition, that means it is a nucleophilic radical, it has undergone addition to the corresponding product. Let me give you 1 or 2 more very important examples, from medicinal chemistry. Okay, some of you probably are familiar with this, again a quinoline derivative. It is an anti-cancer drug, and what you will see, it has so many functionalities, and it has only one chiral center, and then you have double bond nitrogen and this, and then you have nitrogen this. Actually I used to know the name, but I do not know the spelling, but it is known as camptothecin, I think camptothecin probably, it is known as camptothecin. Camptothecin, I think, if I am incorrect I will correct it next class, but name is although important, but for us now the reaction is important. So, how would I, or rather how would we functionalize this molecule and chemoselectively, regioselectively with a methyl group at the 4 position up here, So, rest remains as it is, Okay. And so, what do you expect, and what should be the recipe, what are the required chemical? Okay, yes, not campto. Okay, now I got the name. It is camptothecin. Okay, this is an anti-cancer drug. Now, many times actually to solubilize, you have to introduce something. You have to introduce a nitrogen. You have to introduce a side chain, and one of the first steps here is the introduction of the methyl group. So, by now all of us know the recipe should be, the starting carbon source should be acetic acid. Acetic acid would give the CH3 radical. So, once you know acid, that means immediately you have to think about the silver salt and all these things, but that is what we would think, right, and then per disulfate. But in this example though, alternatively, see if you recall, there is another possibility also, this Fenton's reagent set also is perfectly all right, ferrous sulfate, then tertiary butyl hydroperoxide and carboxylic acid, and sulfuric acid is also equivalent, also serve the purpose of producing this CH3 radical. Let me give you one more example. This example is applicable to the imidazole derivative. Imidazole derivative with a double bond isopropyl group here and a nitrogen containing side chain, that means NH and this and the corresponding ester here. Now, what you see, and the set is same thing, that silver nitrate and then per disulfate and etcetera, etcetera, etcetera. But eventually what you will get? You will get this imidazole, that basically histidine, right, histidine moiety, and then you have this, that, and what is this cyclopropane carboxylic acid. So, it is equivalent to, so this set of silver nitrate, per disulfate, etcetera, etcetera, would be equivalent to cyclopropyl radical, right. So, that is the beauty. That means, I mean nowhere in the chemistry we have seen a cyclopropyl radical. Okay. Cyclopropyl methyl radicals are known, but this radical is not that commonly used. Okay. And so, you can generate that. Now, mind it that you have a 5 membered heterocycle, 5 imidazole, and that can be functionalized, and in this case the middle one, the number 2 carbon, is functionalized with a cyclopropane. So, where do you see cyclopropane moiety? In medicinal chemistry. In fact, many of you know norfloxacins. Norfloxacins, have you heard of norfloxacin? They are basically this second generation, third generation of antibiotics. They have, what are the heterocyclic moiety present in norfloxacins? Quinolone derivatives. Okay. And in market you will find there is a cyclopropaquinolone. In fact, cyclopropane can be placed in the place in the nitrogen, and those are also pretty useful. Then if you have a real bulky radical, you can also make use of it in radical chemistry. Then there are other usefulness of these radicals could be for the introduction of trifluoromethyl radical. Okay, trifluoromethyl radical. If you take trifluoromethyl iodide and use Fenton's reagent, you can produce the corresponding radical, and that radical can undergo addition to many heterocycles. I mean, in this example, I have with me, it adds to these nucleic acids. Okay. So, similarly, there are cases examples, there are known examples where you can also functionalize furan. Many of us know furan is acid sensitive, but in that case you have to change the reaction conditions. So, what can you do? See, all of these reactions actually involved use of acids, because you have to protonate the nitrogen and have to make this heterocycle more regioselective. But in case of furan, which are more, very susceptible to acidic conditions, then you have to change over to something else. Okay. Recently, people have used phenyl boronic acids. Phenyl boronic acid in the presence of something else, again a different kind of oxidizing agent, manganese triacetate. So, in the next class we will see some of the special cases, like how to generate radicals from manganese triacetate, and many of you probably know the phenyl iodinium diacetate also is exclusively used these days. Then in classical literature, people used to use lead tetraacetate. For example, you have cyclopentane 1,2 dicarboxylic acid. How do you produce cyclopentene from there? Lead tetraacetate. The principle is basically, then lead tetraacetate also used for remote functionalizations. If you have an alcohol, then you use lead tetraacetate, you can make use of the reactions in. Okay. And I think we will have little different kind of radical reactions. How to generate heterocyclic, these are all for the functionalization of the heterocycles. In the next class, we will have some examples where how to construct the heterocyclic ring by using